of deformation. And I would just like to recap some of the important principles using this picture that I made yesterday. The tomatoes used to be circular, or almost completely circular, and now they are elliptic. And so you can say this whole thing was deformed. You could probably write down the deformation tensor, the D tensor for all of these tomatoes, and you would then start to wonder, was this a homogeneous deformation? And this is actually quite a good picture to start to think about this a little bit deeper, because of course the deformation at the scale of the tomatoes is not very homogeneous. It is made out of these little movements along the cuts. But yes, the form of the tomatoes resembles an ellipse. Okay, so if you look maybe a little bit from the back, you could say that we almost have some kind of a representative elementary volume, more or less homogeneous deformation. But then if you look at the deformation of all these tomatoes, you will again find out that deformation must have been very heterogeneous, because there is no way that you could transform a series of circles into all these ellipses in a homogeneous deformation. So again, D-tensor and homogeneous and heterogeneous deformation as a question of scale. You have to really consider what scale you need to describe deformation as homogeneous. The D-tensor is a very simple linear transformation that transforms a circle into an ellipse, and it really just describes the change in shape, the deformation. Today we are going to talk about stress. And can I put this away and get us this PowerPoint presentation. We will talk about stress, and stress is of course very important. Stress is a very, very central concept in mechanics. Stress is all around us. If I stand on this floor, the stress in the floor changes. The moment you stand up, there is stress in your bones, and there is basically stress everywhere in solids around us, not just in rocks, but in biological materials, in engineering. So the concepts of stress, again, are treated in many courses in the RWTH, and you will be able to talk about stress with your friends who do engineering when you go to the bar and you feel like talking about stress. So there will be things about stress vectors. I will tell you about the stress tensor, and what you will learn is that the mathematics of stress tensors are exactly the same as the mathematics of strain, but the physical meaning is very different. And then of course talk about friction, because that is an essential part of deformation of dynamics in the upper crust. I will talk about effective stress, and I will talk a little bit about how stresses are in the earth. And some of these concepts I'm going to illustrate. There's a number of very simple examples. I will bring these in the next lecture again when I talk about mechanical properties. Okay. So just to bring the point home, I made this picture, I downloaded this for you from the website of the United States Geological Survey. This is California. You see the city of San Francisco, Golden Gate Bridge, Alcatraz, and these are the coastal mountains. This is Half Moon Bay, and the red lines here are traces of the San Andreas Fault. I will talk about the San Andreas Fault in one lecture later on in the tectonics part. The San Andreas Fault is not moving constantly, but the earth below the San Andreas Fault is moving, the plates are moving, and the San Andreas Fault locks up. It is increasing the stress which is stored in the rocks, and then at one point it breaks, and you can get very large earthquakes which are predicted to destroy the city of San Francisco within the next 50 years. So stress is important. Just like with strain, if you want to start understanding stress a little bit, you have to go back to very, very first simple principles. So we will start with the stress vector. Okay? The stress vector is something which is defined in mechanics. It is a pair of stresses which act in opposite directions and in equal magnitude across a plane. You could say that the stress is built up from the forces which act on this plane. Of course, for the equilibrium, you need to have these exactly opposite. And if you divide on which it acts, then you get stress. So stress has the units of pressure, like Pascal, Newton divided by square meter, or megapascal, which is 1,000,000 Pascal. There is a typo here, this should be a big P. And pound per square inch is one of those wonderful British units which is quite a lot used in the industry. So, for having stress, we need to define the plane on which the stress acts, and we need to define the stress as a vector. It has a direction and a magnitude. This stress vector can be decomposed in a number of different ways. And one of the confusing things about this lecture, that is where you really will have to pay attention, is how you decompose the stress vector. I will decompose it in today's lecture in several different ways. So here's the plane, and the plane is defined by its normal. Okay, so this is the plane, and this is the plane normal. That is the thing that you use to plot in the stereogram the position on the plane as a point. And in this case, here we have the x1 and the x2 axis, and this is the stress vector on the plane. We can decompose it in its x1 and x2 components. We have done this before. But I can also decompose the stress vector in the normal and shear component. That my reference frame is the plane on which the stress is acting. Now, you might ask, why do I want to do that? The reason is actually quite simple, because normal stress and shear stress are the basic parameters which determine friction. You have all learned about friction in the secondary school. It is the normal stress and the shear stress which play a central role in friction, and friction is very important in the Earth, and therefore it's useful to decompose the stress vector in normal and shear components. If I have a plane, maybe a fault plane in the Earth, for example, or just a sheet of paper, then it is actually not so difficult to conceptualize, to understand the notion of this stress vector. It is simply the force divided by the area. What is more difficult is trying to figure out in this direction and in this direction. There are infinitely many planes in this piece of solid, and on each of these planes you could try to figure out what the stress vector is. So my next slides are going to illustrate this question in a little more detail. Let's assume that we have a piece of solid, so it must be strong and it shouldn't break. We'll talk about breaking later, but now it is just solid. And I'm going to put a vertical stress of 2,000 pounds per square inch, it doesn't really matter what units I use here, on this side, exactly normal to the face, so I'm not pushing in any oblique direction. I do the same in this one, and here in the horizontal direction, I put 1,500. So, the cube is in equilibrium. I think you all agree. The forces are exactly in equilibrium with each other. The cube doesn't fly away, it doesn't start to spin in any direction. So it's in equilibrium. And my question is now, let's assume that there is a plane, this blue plane, inside this cube. It's imaginary. And I'm asking you the question, what is the stress vector on this plane? One way to visualize this would be to think about this block. Okay, I'm pushing so much, this 2000, I'm pushing this 1500 in this horizontal direction, and now I cut this block in two, and I put instantaneously a stress vector on one half of this block and take away the other half without that this side notices it. Okay? Then there is exactly equilibrium with the stress vector on the plane and all the stresses which act in all other directions. So basically, I take away the block which is pushing back and replace it by a stress vector without the other side noticing. That is the stress vector on this plane. So, what is the stress vector then? Well, in this very simple example, it's not so difficult to figure it out. Any forces which come from the vertical direction have no effect on the plane at all, because they are parallel to it. So, the stress vector on this blue plane is horizontal, and it is exactly 1500. This vector is just put onto that plane. Okay. It's exactly the same difficulty as the next question. I put in a horizontal plane, and I ask you, what is the stress vector on this plane? You think a little bit, and you very quickly come to the answer. It is vertical, exactly normal to the plane, and magnitude is 2000. Okay, so far so good, not very difficult. But now comes a much more difficult question. I now put my plane at this angle into my cube. Maybe I put it all the way from one side to the other. I have this stress, and they are all pushing. And I ask you, what stress vector do I have to put on this plane so that I can take away this half, and the other half doesn't notice? That is the stress vector on the plane. Okay. So, what I will do now is I will show you a very brief, short version of the derivation of Cauchy's law, which is the derivation of the stress vector, or the stress tensor rather. The way it starts is this. Our cube was stress defined by stresses which are normal on its four faces. This is in fact a special case. I can also define the same cube in a little bit different orientation where there are normal stresses and shear stresses on each of its faces, and it is still in equilibrium. So I just ask you to imagine a situation like this. The cube is in equilibrium, it doesn't start to spin, it doesn't fly away, and all these forces, all these stresses, keep it in equilibrium. That is the starting point of the derivation. What I will do now is I switch off the beamer. Could you do that please for me? Or make it dark. So I start with my coordinate system. Would you like to start again with the video?
It's okay.
Okay, so I start with defining my coordinate system, x1, x2. Nothing new there. And then I put my little cube in it. And I put all these arrows, stress vectors, on this place. Here. Exactly the opposite on this side. There's one there, let's make it a little smaller. Exactly opposite.